Alright guys, so we're going to start with neutralization reactions. I may have gone over this briefly with us during CAP review. It should only take us a few minutes to go through. So imagine I have an areneous acid such as HCl aqueous, hydrochloric acid. And let's say I mix that with NaOH, which is an areneous base. This is basically a double replacement reaction that we're seeing. Could someone tell me what is one product we get from this in a double replacement, Ian? Quinn?
Cl plus, it'll be Cl plus NaOH.
Not quite. Look at what ions we have. We have a hydrogen, we have a chlorine, we have a sodium, and what is this? Hydroxide, right? So Ian, what are we going to get?
You're going to get H2O and NaCl.
Good. So the Na goes with the Cl, the H goes with the OH, so it's HOH or H2O. And this is the basic formula of a neutralization reaction. Why do you think we call it a neutralization reaction, Mike?
It neutralizes the acid.
Right. We start with a strong acid, HCl. We start with a strong base. Two things that could kill you if you drank them. Mix it together. Salt water. Okay. The general formula for neutralization reaction is acid plus base yields water plus salt. Now in this example, the salt is like the common term for salt, NaCl. But salt really just means any ionic compound. So, you know, it could be calcium carbonate, could be lithium sulfide. This one happens to be NaCl. Yes, Ian?
So when you have something like hydronium ions being formed, like with H3, is that technically still water being formed? Or is that...
No, hydronium is not water. In this case, you're not actually forming hydronium because it's not reacting with the water, it's reacting with the other thing. If I just took HCl, dumped it in water, you'll get a lot of that hydronium forming.
Then it's not an acid-based reaction.
Right. This is an acid-base reaction, neutralization reaction. By the way, in order for this to work, what type of acids does this acid or bases do these have to be? Areneous or Bronsted-Lowry? Areneous. Can you tell me why?
Because you said it in the beginning. You said these are areneous.
Okay, thank you. Let's look specifically at the base, guys. What do all areneous bases have in common?
They all have OH.
Right. Remember, we talked about a lot of different Bronsted-Lowry bases. They don't need hydroxide. Like NH3 is a Bronsted-Lowry base. F- is a Bronsted-Lowry base. You can't get this reaction with those. It needs to be an areneous acid, or areneous acid and areneous base because you need a hydroxide. It's a US, not OUS. Okay. So that's basically for neutralization reactions. Very simple concept. That's why, you know, if anyone in here ever spilled very strong hydrochloric acid, the way I have to clean it up is I have to pour base on it. I can't just pour it down the drain. Pour base on it. It you know, neutralizes it.
Could you drink the water technically?
Well, that's a funny question. I kind of brought this up to the other class. If you trust your glassware, and you trust your acid, and you trust your base, which if you're ever going to drink anything, you just never assume that. But theoretically, in the perfect world, if you had a perfectly stoichiometric condition here, yes, you could pour acid that could kill you, base that could kill you, into your mouth at the same time and live, theoretically. When?
What if you did it, like you're like, hey, I'm gonna drink this and it'll kill me, but like right before that you chugged some like base that would kill you and you did it like
Can't do
so
one
it was like
first.
boom boom. It was like right away. And then they mixed
Well, the
together
thing is,
right before
you got to realize your throats can be lined with killer base, you know, before the acid comes. What I'm saying is, stoichiometrically, yes, it works. In the real world, no, it would not work. You would die.
Yes.
Try.
No, we can't try. Okay?
That'll be fine.
I'm just saying, theoretically, you could. All right, let's talk about pH and pOH. So this is more continuation of our acids. Keep in mind this stuff's not going to be on tomorrow's quiz, but it will be in the future. Alright, so I want to start introducing pH and pOH by talking about what water naturally does when it's in a beaker. I mean, pure water is never really just pure water. Imagine we have a reaction with H2O liquid plus more H2O liquid. Every now and then these are going to react where this water is going to basically pluck a hydrogen ion off of this one, leaving us with H3O plus aqueous and OH minus aqueous. This is something that happens very rarely, but if you have a beaker of water, we're talking about 10 to the 23rd molecules of water. It's there's going to be a lot of hydronium and a lot of hydroxide in water. And the reason this happens is because is H2O a perfect, evenly distributed molecule? No, it has a partially positive oxygen, two partially negative, mix that around, partially negative oxygen, two partially positive hydrogens. So if a water molecule happens to strike another one with just the right amount of speed and at just the right angle, it could pull a hydrogen off, leaving a hydroxide. So the point I want to make with this is this happens very rarely. Okay? The figure that we've kind of realized, it depends on temperature. In fact, pretty much every reaction, the rate of reaction depends on temperature because, like I said before, in order for something to react, you need it to kind of hit the other molecule at the right speed and at the right angle. What happens to something if you heat it up? Good. Particles move faster, so all of a sudden you have a lot more of them potentially going fast enough. It's also why when you heat something up, you can dissolve more things in it. Anyway, this happens very rarely, and we found that it's about 1 in 10 million water molecules at any given time are split up. And one thing I forgot to write here, this definitely goes both ways. It splits up, it reforms, splits up, reforms. And it's like instantaneous pretty much. Splits up, reforms, splits up, reforms. So it's about 1 in 10 million water molecules happen to be currently split up and then instantly goes back. And this leads us into this idea of pH and pOH. Okay? So, I'm going to kind of change up the order I gave this in. Let's see if this will work better. Yep.
So, is there a specific acid base for that?
For this one, no. Technically, one is acting as an acid, one is acting as a base. But really, this is just introducing what I mean by pH and pOH. Okay? pH. What do we think of when I say pH?
The scale.
The scale, strength of the acid. Yeah, acids. Are acids low or high pH?
Acids are
Low pH. Low pH. Here's what pH actually means. Negative log of the hydronium ion concentration. Okay? This bracket here. Brackets means concentration. That's kind of a chemistry symbol that we use. So this means concentration of hydronium ions. This obviously means concentration of hydroxide ions. Okay, so a negative log of the hydronium ion concentration. Let me write that out in words just so we're all very clear about this. pH equals negative log of the hydronium ion concentration. Who has worked with logs in math class? Who has asked your math teacher when we're ever going to need to use this stuff?
No.
Yes.
He already said
Typically,
it. He said
that
it.
question
Here we are.
Yeah.
is just doesn't get answered.
It's a very annoying question for you to
Yeah.
ask a teacher.
I don't ask it.
Good.
It's like
I'm
it's
I did.
So what
He
measures,
says it. He says
hydroxide ions is the
Yeah,
pOH?
Yes. We'll get to that in just a minute. Okay? Guys, quiet down, please. So pH is a negative log of the hydronium ion concentration. Let's talk about what logs actually mean. We'll do kind of a crash course in logs. Well, first of all, a log is short for a logarithmic. Does anyone know what the difference between a logarithmic scale and a linear scale is?
Log is by 10.
What was that?
The logarithmic one is by 10. Or goes by
That's exactly it. Linear scale is completely linear. It goes up by 1. Logarithmic scale, if you go up 1 unit, it's 10 times the value. Anyone know, what does a Richter scale measure?
Earthquakes.
Strength of earthquakes, that's a logarithmic scale. Meaning a magnitude 7 earthquake is 10 times stronger than a magnitude 6. The one that just hit in Nepal was a 7.8, so that's almost 10 times stronger than magnitude 7. I think the highest one I've heard, at least in my lifetime, was off the coast of Chile, a couple years ago. It was like an 8.4.
wow.
Which compared to the one in Nepal, which the death toll's up to like 10,000 now, the one off Chile was like, had to be at least 5 or 6 times stronger. I mean, it's logarithmic like that. So pH is a logarithmic scale. What the word log here actually means,
Oh no, oh, I thought you were talking about log, yeah, of course.
what this means is 10 to the what power equals this concentration. 10 to the what power equals that concentration. Now let me just do a quick example without this. Log of 1,000. This means 10 to the what power equals 1,000. Can anyone answer me that question? 10 to the what power equals 1,000?
Third.
10 to the third. So type in your calculators real quick. Find the log button. Do log 1,000, close parentheses. You should get 3.
Too bad that one doesn't have it.
Three.
Yeah. It's 3.
You're going to have to do a very minimal amount of logs. But yes, we are doing logs. Okay? So log 1,000 means 10 to the what power? So 3. Okay? How about this one?
Can we use food calculators for this?
What's that?
Can we use like our regular school calculators?
I will decide that later. The department, we generally use these ones for consistency. This one. So what this means is 10 to the what power gives you 0.01. Negative 3, I don't think it's that. I think it's negative 2, right? 10 to the negative 2 means 1 over 10 squared, 10 squared being 100. So that's 0.01. So this answer, you type it in, it should give you negative 2, right? Just try it real quick, make sure we're on the same page. All right. So now that we kind of have a basic idea of what logs mean, and really the reason we use logs is because it's a much easier way to express it. Like, if we didn't use logs, I would have to give you an acid and say, okay, be careful, this is 1 in 10 million hydronium ion concentration acid. Since we use logs, I could just say, okay, careful, this is pH of 7 acid. Okay, it's a much easier way of expressing it. Let's revisit this this example here. Did I actually see? Right here. So for neutral water, okay, this happens very rarely. 1 in 10 million water molecules happen to be a hydronium. Yes?
You explain what the product means.
This?
Yeah.
This means that on a very rare occasion, this water will collide with this water in the perfect angle, direction, speed, and basically this oxygen is partially negative. The hydrogen is partially positive. If it hits it perfectly, 1 in 10 million chance, this oxygen can basically steal the H+, leaving this one with H3O+, this one with OH-. All right. So, whoops.
So will that give us the pH of water?
Well, let's work through it. So remember, pH equals negative log of the hydronium ion concentration. What did I say is the hydronium ion concentration, or how frequently does that occur? 1 in 10 million, okay? So for regular water, this is 1 in 10 million. Another way we can express this more numerically is 1 over 10 million. Or in scientific notation, anyone can do this quickly? What would that be? 1 times 10 to the
7.
not 7th, negative 7th. Okay? Because 10 million, that's 10 to the 7th. 1 over 10 million, 10 to the negative 7th. Well, let me put it this way. Equals 1 times 10 to the negative 7th, or an even simpler way of writing this, take out the 1, 10 to the negative 7th. So in other words, for regular water at room temperature, the concentration of hydronium ions is 10 to the negative 7th, meaning for every 10 to the 7th water molecules, there's 1 hydronium. pH equals negative log of 10 to the negative 7th. Before you plug this into your calculator, this means, first of all, log 10 negative 7 means 10 to the what power gives you 10 to the negative 7th power? Right, it's very simple. 10 to the what power gives you 10 to the negative 7th? Negative 7. pH equals negative 7. What is pH? 7. Let's double check that on the calculator. Negative log of 10 to the negative 7. It should come out to 7.
Now I get negative what?
pH is negative log of 10. You might need to use parentheses after your caret.
Got it.
We all clear on this? How we do this calculation? Yep.
Yeah.
pH equals negative log. Right, pH equals negative.
What I mean by this is, look, if pH just equaled, hey guys, quiet down. If pH just equaled log of 10 to the negative 7, what is this? 10 to the what power gives you 10 to the negative 7? Negative 7. So this would mean pH equals negative 7. Well, negative 7 doesn't really work for pH. So pH equals negative log. So we just take the number we get, switch it to a positive, that's our pH. So for neutral water, pH equals 7. You guys probably knew that. You knew pH of neutral is 7. Now we know why. It's because in regular water, every 1 out of 10 to the 7th water molecules is hydronium ion. So therefore, that 7 becomes our pH. Let's do another example. Let's say you took that same water, which was 1 in 10 million. We add HCl. Guys, come on. One more. Let's say you add enough hydrochloric acid so that, well, let me put it this way. Would the new concentration of hydronium ions be higher, meaning like 1 in 1,000, 1 in 10, or would it be lower, like 1 in 100 million? If you added HCl.
Higher.
Right, it would be higher. Because remember, this is going to split up into H plus and Cl minus. What's that H plus going to do when it gets in water?
It's gonna bond to it, it's gonna make hydrogen.
Right, it's going to find a water, latch on. So this means higher concentration of H3O plus. And in this example, let's say you put enough that the pH increases by 1,000 times. So it was 1 in 10 million. What would it be now? 1 in what? 1,000 times more.
1 in 10 billion.
Nope, other way. 1 in 10,000. So now the new estimate, we're just going to make this up. 1 in 10,000. Okay? So we've made it 1,000 times more acidic. All right, let's find the pH.
How did you make it a thousand?
By adding HCl. We dumped a whole...
Do that?
Look, because HCl becomes H plus and Cl minus. The Cl minus just sits there. Well, not really, but it doesn't incorporate into the acids. The H plus is not just going to sit there. It's going to find a water, attach to the water, and increase your concentration of H3O plus. Okay? pH equals negative log of the hydronium ion concentration. What is my hydronium ion concentration? 1 in 10,000. 10,000 can be written as 10 to the negative what? Fourth. So, well, technically 1 in 10,000 is 10 to the negative fourth. 10,000 is 10 to the fourth. So this means my pH equals negative log of 10 to the negative fourth. So without even using your calculator, 10 to the what power gives you 10 to the negative fourth? Negative 4. What's negative negative 4? 4. So my pH is 4.
What's the log of negative? Wait, so how is the log of negative?
Because log of 10 to the negative fourth gives you a negative number. But because we don't always deal with negative numbers, we just make the answer negative. And as well, the reason the log ends up being negative is because 10 raised to the negative something power gives you a really small number. 10 raised to the something positive power, that's when you get your 10 million, your 100 million, your billion. But if I want 1 in 10,000, or 1 in 100 million, or 1 in 1 trillion, I have to deal with negative numbers. So like 10 to the negative 9th, that's 1 billionth. So when I say it's 1 in 10,000, that's 10 to the negative 4th. So the log of 10 to the negative 4th is negative 4. Because we don't always deal with negatives when we talk about acids, we just say negative log gives us our pH. What?
How did you go from 10 million to 10,000?
I just made this up in an example. I said, assume we started at our regular water. Let's say we added enough HCl that it turned 1,000 times more acidic and went to 1 in 10,000. Okay? So we started with a pH of 7. We ended up with a pH of 4. I told you it got 1,000 times stronger, right? Thinking logarithmically, this makes sense. Going from 7 down to 6. How many times more strong? 10 times. 7 to 6 to 5 is how many times more strong? Not 20. 10 times 10.
Oh my god.
100 is logarithmic. It's not even exponential. It's more quickly rising than exponential. So 7 to 6, that's 10 times. 7 to 5, 100 times. 7 to 4, 1,000 times. So when I say I increase the acidity by 1,000 times, I went from pH of 7 to pH of 4. Is this making sense? See, we're doing logs and we don't even need calculators. That's what's, good about this.
Wait, but how do you know when you add the HCl that it changes it to 1 in 10,000?
I just made this up. In the problem, I will either give you the pH or I'll give you the concentration. Okay? Now, let's do a little bit more here. So, something we know about water, just from, decades of experimentation, is that the concentration of H3O plus times the concentration of OH minus always equals some constant number. Okay? It's always constant, meaning if this goes up, what happens to this?
That will go.
Goes down. Okay? If one goes up, one goes down. Okay? Now the first example I gave for regular water, what's the concentration of this? 1 in how many? 1 in 10 million, right?
Do we need to memorize like that?
No, get it down in your notes for now. Once we readdress pH after the quiz, I'm going to give you a sheet with certain equations. But I want us to understand the basics of this. Yep.
Actually, I have a question about this whole thing, really. Like, if it happens really rarely, why are we going so fast?
What I mean is, hydronium ions in water happen rarely, but anytime you have an acid, this is happening. Like, what I'm saying is, it's not like half of all the water happens to be split up. It's like 1 in 10 million. But even if you're 1 in 10,000, if you drink water that has 1 in 10,000 hydronium, you're dead. Like, that's why, you know, even though it happens rarely, it still happens so much that all of these acidic properties still matter. Okay?
I could die from drinking water by chance.
No, because natural water would never reach 1 in 10,000.
It's 1 per million.
I mean, acid rain has a pH of around 6, so that's 1 in 1 million.
Could that, if you drank that, can that cause that effect?
It wouldn't be that bad. Yes.
Use this to what, 1 in 1 is? Like what one of these?
It's,
You might die.
guys, quiet down, please. Quinn. What I mean by like the 1 in 1 million, 1 in 10 million, that means that the concentration of H3O pluses in water is that. So if it's 1 in 10 million, it means 1 in every 10 million water molecules happens to currently be split up into H3O plus. Okay? So it happens rarely, but it's enough that it matters. Okay? Let me go back to this. The concentration of hydronium ions times the concentration of hydroxide ions is always constant. And through experimentation, we know what this value is. It's 10, well, let me do it more precisely with sig figs. 1.0 times 10 to the negative 14.
And what does that represent?
It represents the concentration of this times the concentration of that. So I told you that this is 1 in 10 million, or 1 times 10 to the negative 7. Now in neutral water, the concentration of this equals the concentration of this. Because assume we have like pure water with no hydronium or hydroxide at all. Never going to happen, but imagine we had that. And then all of a sudden, one water molecule splits up. For every one of these, how many of these do we get? One.
Yeah, one.
I mean, going way back to this. For every one water that splits, we get one of each. So in neutral water, in water with a pH of 7, this equals that. So this is 1 times 10 to the negative 7th as well. Multiply these together. You add the exponents. What's negative 7 plus negative 7? Negative 14. You don't multiply it. Okay? So in other words, concentration of hydronium ion times concentration of hydroxide ion always equals 1.0 times 10 to the negative 14. This number here is called the ion product of water. And its symbol is K with a little subscript W. And that equals 1.0 times 10 to the negative 14. Now this does change. As the temperature of the water changes, it changes slightly. But we're going to always assume that it's this value. It's very easy to work with.
So that represents the constant of water.
What this is trying to show is that as hydronium ion increases, hydroxide ion decreases at the same rate.
But isn't that very specific because it's like two very specific?
Well,
So that's only true. That's only true when in a 1 in 10 million thing, right?
no, let me work through this example. So this was neutral water, right? The second example I said, what was the pH of the water? And that second example I made up? 4, meaning it was 1 in how many? 10,000, or 1 times 10 to the negative 5th. Well, if this went down by a factor of 1,000, this must have done what? Gone up by a factor of 1,000. So this would now be 1, I'm sorry, I said down, but technically when you go from negative 7 to negative 4,
You're going up.
you're going up. This is 1,000 times more than that. So technically this goes down. So I'm going to go from -7 down to -10. 1 times 10 to the -10th. What does this equal when you multiply it? 1 times 10 to the
Wait,
-14.
why did that one go down by 1 and now the other one went down by?
This went from 7 to
and
4.
went up by 3.
This went from -7 to -10. It's
Why?
three numbers here represents 10 times 10 times 10.
But why did it do that? I'm confused how you're getting from -7 to -4. I understand that one goes up and one goes down.
Yep.
But I'm wondering where you're getting
The numbers, I pulled them from the 2 examples that I've done so far. The first example, I said imagine you have pure natural water, pH of -7, right? Then I said imagine you dump HCl into it and it goes up 1,000 times in concentration. You see how this is 1,000 times more? So therefore, the concentration of hydroxide started out as 10 to the -7th. It dropped by 1,000 times.
Oh, okay. Yeah.
Don't get hung up on this. I'm just trying to transition this. I don't want to just give you guys 10 formulas and then just say go. I want to try to transition through this. Okay? This leads us into pOH. Now, pH is negative log of the hydronium ion concentration. I think Emma said it earlier. What do you think pOH is? Negative log of the
Hydroxide.
hydroxide ions. Of the hydroxide ion concentration. Okay? So let's work through the 2 examples that I gave. For the first example, neutral water. pOH is negative log of the hydronium ion concentration. In neutral water, which was this example, what is my hydronium ion concentration? Sorry, I'm mixing up my terms. Hydroxide ion concentration. The value is this, right?
1 in 10 million.
1 in 10 million or 10 to the -7. Okay? So for neutral water, pOH equals negative log of 10 to the -7. 10 to the what power gives you -7? -7, so it becomes 7, right? So pOH equals 7.
Wait, doesn't that mean that there aren't? What is it? Isn't that acids have a lesser
Right.
scale? So
Okay.
don't you have to make it-
So first of all, let's talk a couple numbers here. We recognize 7 as neutral acid, right? Neutral acid to neutral base. What do we recognize 14 as? Because this number comes into play too. Right, it's like the maximum a base could be, right? Here's where we see these numbers. In my first example, pOH equals 7. Thinking back, what did we say pH was for neutral water?
7.
Right. 7 also equaled pH. Because we say the concentrations of them, one goes up, one goes down, this works. Here's your formula. pOH, well, we always say pH first. pH plus pOH always equals a constant number. What number? 14. pH plus pOH equals 14. Now remember, that 14 means like a logarithmic total. Meaning, altogether, we're talking about 10 to the -14th concentrations. So for neutral, it's 10 to the -7th of this, 10 to the -7th of that, multiply the exponents, 10 to the -14. Let's work through our second example. So, second example, we said 1,000 times more acidic. We calculated that the new hydronium ion concentration was now 1 in 10,000, which equals 1 over 10,000, which equals 10 to the -4, right? pH equals 4. This is just review. We did this already. Let's work out mathematically the pOH, and then we'll check that sort of shortcut I said. Well, if H3O plus times concentration of OH minus always equals 1.0 times 10 to the what? -14th. if this is 10 to the negative fourth, this must be 10 to the negative what?
10 to the
Negative 10th. So therefore, concentration of OH minus equals 1 times 10 to the negative 10th, or just 10 to the negative 10th. 2 seconds and we'll finish this, trust me. pOH equals negative log of the OH minus concentration, which equals negative log of 10 to the negative 10th. What's my pOH going to be? 10. So in other words, 10 to the what power gives you 10 to the negative 10th? 10. Okay? So pOH equals 10. Does this fit my rule? 4 plus 10, 14.
Yes.
Checks out, right?
Yep.
Okay, take a break.